Welcome back to our series on the major components of the gas turboset. Up until now, we have focused on the prime mover, the gas turbine itself, which transforms fuel and air into high-speed rotational energy. But how does that spinning shaft actually light up a city? In this segment, we move from the mechanical to the electrical. We will explore the generator, the massive component coupled to the turbine shaft. This is the final stage of the energy conversion process, where the kinetic energy of the rotating turbine is transformed into the electrical energy that feeds the power grid. The primary elements of the generator assembly are detailed in the following section. The casing serves as the structural frame, housing and securing all internal generator machinery. Constructed from welded steel plates, this horizontal, cylinder-shaped enclosure rests upon a heavy-duty welded foundation, which is securely anchored to a concrete base. To facilitate maintenance and assembly, the housing features a horizontal split along the center axis. Internally, the structure is equipped with specialized ribbing designed to precisely direct the flow of cooling air across the internal components. The stator is designed as a rigid, self-supporting core composed of numerous thin laminations divided by integrated ventilation channels. These laminations are crafted from high-efficiency, low-loss electrical steel sheets, each individually treated with an insulating varnish on both surfaces. This insulation is critical for suppressing eddy current losses and eliminating localized overheating hotspots. To ensure durability during operation, the entire core assembly is mounted within the stator housing via a spring suspension system, which effectively absorbs mechanical vibrations and allows for natural thermal expansion. The stator winding is configured as a two-layer, three-phase system employing an indirect cooling method. It is constructed using specialized Roebel bars, which are fitted into longitudinal slots distributed around the inner perimeter of the stator body. These bars are secured firmly within the slots by dedicated slot wedges. The end windings, which extend past the core, are shaped into a circular cone and supported by trapezoidal insulating blocks bolted to the pressure plates. To protect the assembly from the massive mechanical stresses triggered by potential short circuits, the Roebel bars are lashed to these supports using high-strength fiberglass cords. Located on the upper section of the generator housing, 6 stator terminals serve as the primary electrical interface. These terminals are linked to the internal stator windings through flexible copper straps, a design choice that prevents mechanical stress during thermal expansion. For safety and durability, the terminals are engineered to withstand test voltages $1.50 times greater than the standard operating outlet voltage. Each terminal features dual parallel connection plates on both the internal and external sides of the casing. These plates function as critical junction points, facilitating the necessary cabling between the internal windings, the external collector busbars, and the system's neutral point. The rotor acts as a rotating electromagnet that receives mechanical energy directly from the turbine. The main body is manufactured from a high-grade steel alloy forging, selected for its superior mechanical strength and magnetic properties. To ensure total structural integrity, the entire component undergoes rigorous ultrasonic testing. Longitudinal slots are precision-milled along the body to house the rotor field windings. At the drive end, a forged flange allows for a secure coupling between the generator and the turbine rotor. To prevent electrical erosion of the bearings, the shaft is grounded via specialized brushes. This grounding system protects against stray voltages induced by the stator's magnetic field, the excitation system, and electrostatic charges originating from the turbine. The rotor winding consists of hollow, rectangular conductors fabricated from a silver-bearing copper alloy. The inclusion of silver enhances the material's mechanical properties at high temperatures. Thanks to a highly efficient axial cooling design, temperature gradients across the radial direction are kept to a minimum, ensuring uniform thermal behavior and preventing internal shifting of the components. This thermal stability allows the field winding to expand naturally without generating excessive mechanical stress, thereby preventing any permanent structural deformation. As a result, the rotor maintains superior operational characteristics even during rapid fluctuations in electrical power demand or grid load changes. The rotor windings are secured within their slots using dovetail wedges, which serve a dual purpose by also functioning as integrated components of the damper winding, or amortisseur winding. This damper system, consisting of the slot wedges and specialized damper rings, is designed to absorb and dissipate the energy generated by asynchronous magnetic fields. By neutralizing these irregular rotations, The damper winding prevents potentially destructive forces and heat from damaging the generator's internal structure during unbalanced loads or transient conditions. Cylindrical rotor retaining rings provide the essential clamping force required to secure the end windings against the massive centrifugal forces generated during high-speed rotation. These rings are shrink-fitted onto both extremities of the rotor's active zone and are axially locked using a bayonet-style mechanism. To safeguard the assembly against potential shaft deflection, the rings are attached solely to the end of the rotor body's active section and maintain no direct contact with the shaft itself. As one of the most mechanically taxed components in the entire generator, these rings undergo exhaustive material and stress load validation. They are manufactured from premium-grade, non-magnetic steel specifically engineered to resist stress corrosion cracking and minimize electrical losses within the end winding area. Bearings are responsible for supporting and aligning the generator rotor in the radial direction. The rotor is cradled within horizontally split, pocket bearing shells housed inside bearing pedestals at each end of the generator. This freestanding, split pedestal design allows technicians to access the bearings easily for routine inspections and maintenance. The lubrication and jacking oil requirements for these bearings are supplied by the same centralized systems that service the main turbine. To maintain a clean environment, the two journal bearings are positioned at the base of the generator housing in a way that prevents oil from leaking into the electrical windings. A double labyrinth seal prevents oil from escaping the bearing housing, while a vacuum maintained within the pedestal prevents oil vapor from traveling along the shaft. Furthermore, the bearings are electrically insulated to block stray currents, which would otherwise cause electrical pitting and surface damage. While these bearings handle radial support, the axial, thrust, position of the generator rotor is controlled by the main thrust bearing, which is typically located on the compressor shaft. Leak air filters are installed to block contaminants and debris from entering the machine along with the makeup air. Small intake ports are located on the face of the generator housing to compensate for minor air volume losses within the internal circulation. These ports are fitted with dedicated filtration media to ensure that any air drawn into the generator remains clean. Air coolers are the primary heat management components for the generator's fully enclosed ventilation system. Within this circuit, end shields are used to direct the flow of cooling air throughout the internal machinery. The heated air is then processed through 4 heat exchangers, which are positioned crosswise at the bottom of the generator housing. The thermal energy is transferred from the air to water, which circulates through either a closed intermediate cooling circuit or an open circuit arrangement connected directly to an external water source.